If you notice that come off and I don't see it, holler at me so I can get it restarted. Because I literally just took the two and pieced them back together at the end, and it was fine with it being 40 minutes long. But it cut me off after 20 for whatever reason. So just tell me if you see an error message pop up there and I don't notice it. That happens. All right, what questions do you have? Which one? Which question 9 on which section? The 1.2? For the winning the series? The reason why you have to multiply by 2 is because you have two possibilities. It's symmetric, right? So if the National League wins, you have 4 National League victories, but you could also have the American League win and do the exact opposite. So if you had something that looked like a win that was, say, national, American, national, that would be one possibility. You could flip it, literally just flip them all, and that would be an American League win. So you just have to double it to count the total number. That's why you multiply by 2. Other questions? All right. Well, let's continue our discussion of Bayes' theorem, which we haven't actually written down yet. We were just working on problems. This one should be a little bit more illustrative, hopefully, of Bayes' theorem of what we're doing, and then we'll write down the actual statement of the theorem, and then I'll never write the statement of the theorem down again. So, all right. So, I guess personally, I just think it's easier to just do the problem rather than writing down the theorem every single time. So this one's got an earn. I don't know why in probability they want things to be in earns, but got an earn. This one has several dice in it, 4 dice in it. 2 of them are normal 6-sided dice. One of them has only the evens on it, and the other one only has 6s on it. You know that you draw a random die, and then you roll it, and you get a 4. It wants to know the probability that you pick the die with only even numbers on it. Okay? So it's a conditional probability problem. So you want the probability of the even number die given rolling a 4. Notice this conditional probability feels backward to start with. And what I mean by that is, if I know that I have the even number die, I can then figure out the probability of rolling a 4. Pretty straightforward, right? But it's asking me the reverse conditional. I know that I rolled a 4. What's the probability that I selected that particular die? It kind of feels backward, right? At least I think it feels backward. So that's what Bayes' theorem is about. And really, it's just an application of our conditional probability formula. It's about flipping the conditional around so that we can actually write it in terms of the conditional that we can compute, right? We can't compute this conditional probability directly, but we can compute the reverse conditional, right? If we flip around the given and what we're trying to find. Okay. So first, we just use our conditional probability formula. Remember, our conditional is the probability of the intersection over the probability of the given. And we're going to use the conditional probability formula to flip the conditional on the top, if you will. So what I mean by that is, let me just write this off. I'll write it at the top so don't scroll off the screen. Remember that your probability of A given B, I've written this several times, is that one, right? Your probability of B given A. Notice your numerator doesn't change, right? It's still the probability of the intersection. It's just the given part, right? So if you multiply both sides by the denominators to clear your denominators, the first one says the probability of A intersect B is probability of B, probability of A given B. The other one is the other way around, but it's still your probability of the intersection. It's probability of A, probability of B given A. And this is what I mean by using the conditional formula to flip your conditional, right? We started with this conditional, used our probability formula to get to here, right? But now I want to use the reverse conditional, the one that I can actually compute. Well, notice in this one, if I think of this as being my B, I have it written this way. But now I've got it in terms of the intersection, I can flip it around using the other one. So we know we can compute probability of rolling a 4 given the even number die, right? We know we can compute that. Since now the given part is the even number die, I also need to multiply that by the probability of getting the even number die. Can we now calculate the top? We can now calculate what the probability of the even number die is. It's 1 of the 4, right? And then given that you have that even number die, where we got door from, let's just got die and 4 mixed together. Once you know you have the even number die, rolling a 4 is going to be what probability? 1/3, right? So on top of this, I know I need a denominator. I'll come back to it. But on top, I know the top is 1/4 because there was one even number die out of the 4 total. And I know once I have that even number die, I've got a 1/3 chance that we roll a 4. So I know what the numerator is. We're actually making progress, right? Before, I didn't have a lot to start on. So I'm kind of trying to go in from around the back, in some sense, right? Flipping it around. Okay. Notice that your denominator here is still rolling a 4, right? But notice that rolling a 4 depends on which die you get, doesn't it? Did you draw a regular die? Did you draw the even number die? Or did you draw the die that has all 6s on it, right? Did I roll, say that again, did I roll the regular die, or did I roll, did I draw? Did I draw a regular die, or did I draw the even number die, or did I draw the die with all 6s? I've split it up into cases. I've split it up into mutually exclusive cases, right? So if I roll a 4, there's only 3 possible ways to do that, right? So the way I could write that is I rolled a 4 and had a regular die, or I rolled a 4 and had an even number die, or I rolled a 4 and had the all 6s die. What we've done is I guess I could underline my hands. What we've done is we've broken up our probability of this event into mutually exclusive pieces, right? I can't draw a regular die, an even number die, and another die with all 6s at the same time. So it's all those mutually exclusive, right? I've broken it up into mutually exclusive subsets where the union is the whole thing. If I put all those pieces back together again, I get the whole event rolling a 4. What we call that is partitioning up the set. Okay? When you break it into non-overlapping pieces, that all union back to the total, you formed what's called a partition. Okay? And all we've done is just break it up then as a probability of mutually exclusive events where we can add them. We have the OR. Okay? Notice now, these can all be written in terms of conditionals just like we did on the top, right? We can do probability of drawing a regular die and then rolling a 4 given a regular die. Drawing an even die, rolling a 4 given even die. Drawing a 6's die and rolling a 4 given the 6's die, right? Just like we did on the top. It's literally the exact same process we did on the top. We're just doing it across the whole set rather than just the one piece. Okay? So just to write that below this in red, this is probability of regular die, probability of roll of 4 given regular die. This is probability of even die. Probability, this is times probability of rolling a 4 given even die. And of course it scrolled off the screen for me because I hit the scroll bar. And this is drawing a 6's die, 4 given 6's die. Getting lazy writing at the end there. This is what Bayes' theorem is all about, by the way. And I'll write down the actual theorem in a minute. But this is the idea. You first write it in terms of your conditional probability formula, and then flip all your conditionals all the way through. That's why I said I'll write down what the theorem actually says, and then I'm never going to write it again. I just do it every single time. As a matter of fact, I had probability class several years ago, did this a whole bunch of times, never knew what the Bayes' theorem was until I taught it first. I'm like, oh, that's actually a theorem. I just thought that's how you did the problem. So, tells you how little I actually write it down. All right, so let's finish this off now with the numbers. This says we can do probability of drawing a regular die. What's your probability of drawing the regular die? 1.5, good. Given that you've drawn the regular die, what's the probability you roll a 4? 1/6, good. Probability that you drew. Notice that the next one is exactly what we have in the numerator, right? Because it's draw even die and then roll a 4 given the even die. And that's always going to happen, by the way. Whatever's in your numerator will be one of the pieces of your sum in the denominator when you're doing this every time. Okay? It will be one of these numbers. Okay. Finally, the last one, draw the all 6's die is 1/4. What's the probability that you roll a 4 if you drew all the all 6's die? 0. Good.
What did you say about the denominator? Sorry.
Oh, I said that whatever is on top will be one of the pieces in your sum on bottom. Always. So it'll always be involved somewhere in the bottom.
You mean like the 1/4 times 1/3 is maybe on the bottom? Or like
whatever you have written up here, so yeah, the 1/4 times 1/3 in this example, yeah, will always be also one of its sums. Yeah. Whatever probability you end up computing in the numerator will be a piece of what you're calculating in the denominator. Because that has to be one of the pieces of your partition in this case. Oh, what does that turn into? Half? So 1/12 on top and 1/6 on bottom, it looks like. Because I got a 12 plus a 12 on bottom. It looks like it's a half. That makes sense, right? Given that if you think about the whole problem, it makes sense that it was a half. You knew you rolled a 4, so could you have pulled the 6's die? No. Well, it's twice as likely as getting a regular die as it was getting the all 4 or the even number die, but you were twice as likely to roll a 4 if you had the even number die. So it makes sense that it should be a 50-50 shot, given that you already rolled the 4, right? It's okay? Yeah, Trace.
Why can't for rolling a 4 you just put 4 over 24?
Well, why would you get 4 over 24?
Because there's 24 like things you could get, and 4 of them
4 of them
are 4s.
are 4s. I see what you're saying. In this case, yes, I think you probably could do it that way because you're just picking the one die. Yeah, I wouldn't say you could do that generally because something get a little bit more complicated. Yeah. Yes, I think in this case you probably could say it that way because you've got. They're all equally likely things to have happened, so there's 24 possibilities. Yeah, and 4 of them are 4s. Yep. That would be another way to think about the bottom. It also didn't illustrate Bayes' theorem for me, so I didn't want to do it that way. But yes, I think in this scenario you could do 1/6. I'd be a little bit careful doing that, generally speaking. It's sometimes hard to make sure that you're not using given information when you don't realize it. Okay. All right. So let me write Bayes' theorem off to the side here. That's a very good question and a very good observation, by the way. All right. So here's what Bayes' theorem says. All right, so let's let A be an event with a partition A1, A2, out to AK. Okay. So again, what this means is that our A is the union of the sets A1 out to AK. Each of your sets are non-empty. And they're pairwise disjoint. It's a lot of math, I know. Okay. It just says that we're splitting our event A into mutually exclusive pieces and making sure that each piece actually contains something. That's what this part is here. That's all that says, all right? So I'm going to break it up into these pieces in this fashion. All right, so what we want to compute in this case is, they actually have the theorem written down in here. Yeah, they do. Okay. So you want to do the probability that one of these pieces, the conditional probability that you fall into one of these pieces given some other event B. Well, using, again, our formula, we know that's the probability of the intersection of those two things, right? But then we can flip it around. This will be probability of the event, the smaller event, times the probability of B given the event. On bottom would have been the Did I do that backward? On bottom, I want. Did I write that backward? This is why I don't do it this way. I want probability of A on the bottom. It's the B that I would have had on bottom here, though. I think I split the wrong thing. I think it's my problem. This is why I don't do it, right? Do the theorem, because I always mess it up when I write it down. Let me. I have my. It's over probability of B. I hate when I mess this up. Sorry. Probability of B would be on bottom, where I have this. They've got it. The letters are backwards. What I see in the book, and now I've got myself confused. Sorry, I'll figure it out here in a second. All right. Again, the idea here was, what did we do? We split this into pieces. Oh, sure. Yeah, okay. These still have intersections the other way around, so I can just rewrite this. Let me just rewrite it. Write it this way. Apologize. This is an I. My apologies. I was thinking about it incorrectly. We have the probability of B on bottom. I can take B and intersect it with each of the pieces that make up my A and rewrite my probability of B in this fashion like we did in the previous example. This is why I don't use the theorem ever. This is, when we do this, this is just, all we're saying is that I can write my B as a bunch of pieces together with the intersections and then break them up as conditional probabilities. I'm not going to expect you to write down the theorem, so I may still have this not quite right. So in any event, let's just go back and do some problems. Right.
We need to like add like something to know like when we want to use it.
When we want to use it, so it's always going to be when you're going to use it when you're trying to calculate a conditional probability, but it feels backward. All right. So let's do another one here. Hopefully, I'll make a little bit more sense of what I mean by that as we go. And I apologize for messing that up. It happens from time to time. All right, so let's see what this problem's asking us to do. You've got two boxes, A and B. You've got red and blue chips in both A and B. You're going to grab the A, something from A, throw it into box B, and then pick something from B. So it says, what's the probability that you chose a red one from B, given that you picked a blue one from A to B? Other way around. Given that you picked a red one, what's the probability you transferred a blue one? Sorry. I said it backward. All right, so if I can think about that, it's pretty easy to do it the other way around. That's kind of my indication that I might want to use Bayes' theorem on this, or get it flipped around. Okay. Is it if I know that I transferred a blue one, can you easily calculate the probability of drawing a red one from B? Yeah, I can do that easily, right? Because if I put a blue one over in B, there's 6 red and 4 blue, and you want to use a red one, that's 6 out of 10. Right? 3 out of 5. So that's kind of my indication that I probably want to switch this around. It's a lot easier to do the conditional probability the other way around. Right? Feels that way, doesn't it?
Could you do that?
Could it repeat which part? So is it easier to compute this the other way around? If I know a blue one was moved over to B, is it easy to calculate getting a red one? Yeah, and so that's our indication here that we might want to switch it around. Okay. All right. So again, the conditional probability is the probability of the intersection over the probability of the given. And then we flip around the top. How do we rewrite the top in terms of a conditional probability?
Probability of blue transfer and probability of red chosen given blue transfer.
Good. And again, this is the conditional that's easier to compute, isn't it? So that's, again, our indication that we probably want to flip it. Otherwise, yes. So remember, we're using their conditional probability formula. Oops. We're using this formula is all we're doing. Right? Okay. So if we move it over, oops, this is intersection. Right? Okay. But it's also the other way around. It's also flipped. Same formula. Okay? That's what we're using. Okay? That's how we're flipping around the top. Okay. How can you get to the basically the bottom is kind of getting to the end, right? We want probability that a red was chosen from B. How can we get to the end? Well, there's multiple steps we can get to the end, right? What are your, in this case, there's two. What are the two steps to get a red chosen?
Transfer red and transfer blue.
Transfer red, transfer blue. Exactly. Those are the two ways that we can get to the end, right? First transfer a red and then pull a red. First transfer a blue and then pull a red, right? So on the bottom, it's probability of blue transferred, probability of red given blue transferred, probability red transferred, probability of red given red transferred. Right? There's only two ways to get to the end, right? What I mean by that is, notice how it's starting, right? You draw something from A, put it in B, then draw from something from B. There's only two ways to get to the end. You either drew a blue one from A, put it in B, and then drew a red, or you drew a red from A and then put it in B. Those are the only possibilities, right? So we've broken it up into those mutually exclusive groups again, which is why we can add up the probabilities together. And then we're using our conditional probability formula to get us those and probabilities. Okay. What's the probability of transfer of blue? 5/9. If you transferred the blue, what's the probability you drew a red? 3/5. Good. Notice that probability also appears on the bottom, right? As I was mentioning before. What's on top you should see is a piece of the bottom. What's the other one?
4/9.
Good. If you drew a red one out of the first box, there's now 7 out of 10 red chips in the second box, right? So it's a 7/10. Whatever that simplifies to. What is that? 30 over 30 plus 28. So 30 over 58. 15 over 29. I added it right. I don't know if I added it right or not. Did they ever think maybe wrong? Is the process making sense what we're doing? What questions do you have on this one? Let's do another one. Because you're all having so much fun with these, I can tell. From what I understand from Dr. Roth, anybody who's in artificial intelligence this semester will be doing this next week after, something like that. Bayes' theorem. It's very exciting. Get in other classes. It's used a lot in data science, for example. All right. We got two underwriting classifications, standard and preferred. Tells you that given a policyholder has a good credit rating, the probability that their preferred is 90. If they have a bad credit rating, probability that's preferred is 50%. Probability, we want the probability that a preferred policyholder has a bad record. Okay, so which part's the given? You got a 50-50 shot, right? Which part's the given? I think the preferred is given too, yeah. Let's think about why. Which way did they give you in the problem, by the way? So the given, we already given bad, we know preferred, right? They gave us that probability, so they probably didn't ask us for the same thing again. But in particular, it says a preferred policyholder has a bad record. So given preferred, what's the probability they're bad? Okay.
I need to say it like that in the sentence before that. It's like,
Say that again.
it says given that a policyholder has a bad credit record, stop making bad credit. I know that
This sentence is saying that, or this is what we're trying to find. We're trying to find it the other way around. Yeah. You're right. The previous sentence does say, given a policyholder has bad credit, that is, the given would be bad in that case. Which is why I said, notice that this is the hard way to compute it, isn't it? Let's think about it for a second about why, before we even do the problem, think about why you might want this kind of probability. If you're trying to set a place like State Farm also has a bank. Banks lend money. They might want to know whether or not you're a good or a bad credit risk. State Farm would also do insurance. If they have access to this person's insurance, they can probably tell if they're a preferred or a standard policy member, and they would know whether or not they have at least if their chances of being a bad credit if they're a preferred policy member would be on here. Now, of course, they're going to have other information as well. But if all they knew was a person was a preferred policy holder, they might want to know whether or not they want to give them a loan. And that could be whether or not it's good or bad. I mean, obviously, they're going to do other variables and have more information, but that's kind of the idea here, right? I have this little piece of information. I know that they're a preferred policy holder as far as the insurance goes. Do I also want to give them a loan? Okay. Again, obviously, that's really, really simplistic because they're going to have credit ratings and those kind of things already. But that's kind of the idea here, right? I'm given a piece of information about the person, the situation, the product. I want to know the probability that something happens based on the information that I have. Okay. And when we know what happens the other way around, again, the idea here is we can do our conditional probability. That would be bad, not banned. Bad and preferred over preferred. And then flip your conditional. How does the conditional get flipped on top now?
Probability preferred given back.
Okay. What's over probability of preferred? All right, so now that we fill out the rest of the pieces, I think we fill out two of the pieces pretty quickly. What pieces can you fill out? Yeah, the preferred given bad is what? Yeah, given that it's bad, it's 50%, so 1/2, good. Probability that the policyholder is preferred, 8/10. Good, because I didn't have to split that one up. They told us that, right? Right? Okay. So how are we going to get this number? Right, two of them, but we need that one. That one doesn't seem to be given to us, does it? Yeah, it was that one. All right, so how do we get the probability of bad? How do we get there?
Something with the probability of having.
Well, so can we think about splitting your bad up into two pieces? Bad and something. Oh, we already have one of those pieces. So let's think about other pieces that we know. What do we know? We know some of these other probabilities. Probability of what? Preferred given good, good. We know that one, right? Is 0.9, which we have not used yet, right? Agree with that? Okay. Notice that we could also break this up using your conditional probability formula. If you do your good given preferred the other way around, pardon me, sorry, this would be what? Probability of good and preferred over your probability of preferred. Oops. we can break this back around as probability of good, probability of preferred given good over probability of preferred. Oops. Right? And we know these pieces. This will be probability of good. Preferred given good was what? 0.09, and probability of preferred again is 0.08. Okay. Looks like we're stuck again, but I think we're in a better place than we were. Here's why. By the way, are we okay with how we got these calculations so far with breaking up the formulas? That's kind of the important part. All right, last little bit then, and I think we're almost there. Here's probability of bad given preferred, probability of good given preferred. Bad and good are complements. So if I add those two things together, what do you have to get? 1, right? So I know if I do probability of bad times this 0.5 over 0.8 plus probability of good times 0.9 over 0.8, that has to equal 1, doesn't it? We agree? Those, when I add those, you're either bad or you're good. Given as long as it's the same given information, those probabilities have to add up to 1. I don't have a choice, right? And then likewise, again, we just said bad and good are complements, right? So what could you replace this with?
1 minus.
Yeah, the 1 minus, right? So I have probability of bad. Well, notice, by the way, I'm just trying to get to this number, aren't I? I guess I do need the number. It's that chunk that we need. Your probability of bad times 0.5 plus 1 minus the probability of bad times 0.9 equals 0.8. I just cleared by fraction. Multiply both sides by 0.8. What do we get? I've got a 0.4 probability of bad, and I would have to subtract over and get a 0.2. We get a half? If I did my arithmetic right. This is negative 0.9 plus 0.5 would be a 0.4. It'd be negative. If I move it to the other side and subtract the 0.8, I got 0.2 equals 0.4 bad.
0.9.
Oh, it's 0.1. Thank you. So it should be I forgot to distribute. Thank you. Try that again. 0.1 divided by 0.4 is a quarter. That's better. Thank you, Austin. See, I told you to check my arithmetic. That's what I try to do. That's what I get for trying to do too many things in my head. Now we're almost done. What do I need to do with that 0.25? Put it back in up there. 0.25 times 0.5, that's a quarter times a half. That's an eighth. An eighth is 0.125. And so you have an eighth times 8/10. So you should get a tenth. You're done. That was long and involved. That was. There's such thing as good example problems, good homework problems, bad test problems. This would be a bad test problem. That's a lot going on. I say it's a bad test problem. This is an actuarial exam review problem. So they do put these kind of problems on actuarial exams, but for our purposes, this would be a bad example. That's a lot of things to try to figure out all at once. testing too many things at once for my liking. Questions on how we're rewriting the formulas, that's the big thing, right? Notice that was what I did. I mean, as far as a test-taking strategy went, if you were going through this as a test-taking strategy, got my conditional probability formula set up, I got to this point and said, uh-oh, I don't know what that is, right? But I haven't used other pieces of information in the problem. So what did I do? Went over here and used the other piece of information in the problem, and noticed that I had complements. And so I made my complement equation, right? Not that today's a good example of it, but the way that math is typically presented is so disingenuous. What I mean by that is no one ever does math the way it's presented in a textbook. You don't go from point A to point B in a nice logical flow. Your professors, when they do their math, and what I've illustrated today pretty well as well, is that you don't do it from point A to point B. You start writing some things on one side, you go off and try to do some other things on another side, you make a big mess of things, and finally you see two things that connect together, you put them together, and you finish off the problem. And then when you go back and write the solution, you make it pretty. Okay? But there is so much scrap paper that gets thrown away before you get to the pretty part. And you don't typically see the scratch paper that gets thrown away. Okay? So don't get frustrated if you don't see how to go from point A to point B immediately in a problem, because that's not how math works. It may be how math is typically presented, but it is not how math works. You can see how many things I throw in the garbage. All right. Anyway, let's do the next one. What's that? So yeah, because the examples are coming out of actuarial exams, so that's why there's so many insurance ones. All right. All right. So let's look at this one. Says you've got an auto insurance policy with deductibles $250, $500, and $1,000. You've got the probabilities of claims in a year and the number of policies sold. Says given a claim is submitted, figure out the probability that a deductible is 1,000. All right. Given claim, probability that the deductible is 1,000. Notice that that's not the probability that you want, that you're not, you're given the probability of a claim, right? And it's asking us for the probability of a deductible of 1,000. Given a deductible of 1,000, you can figure out the probability of a claim easily. It's written there for you, right? So that's why we want, this is what our clue is, that we might want to flip around the probabilities, flip around our conditional. If I know the deductible is 1,000, I know what the probability of the claim is. Right? Does that make sense? But this is asking us the reverse question. All right. So the problem is asking us, deductible of 1,000 given claim. Using our conditional formula again. Given our conditional equation formula again, what would we write this as? Okay, good. Writing the top as the reverse conditional, what would the top look like? Okay, good. That's flipping it around, right? And we know this one, right? We know this one. It's not explicitly given to us, but this one's not too hard to compute. How would you get the probability that you selected a claim that, or excuse me, selected a policy that had $1,000 deductible?
900 over the total policies.
Good, 900 over the total policies, right? Was that 2,300? So you do 900 over the 2,300, the total sold. So that one's not too bad, right? So I can do the top. Now let's think about the bottom. I need the probability of a claim. I like to think about it as paths. If you're used to doing trees, it's kind of a tree idea as well. How can I get to submitting a claim? What routes can you get to submit a claim, given the policies here? Yeah, if you go through a 250 deductible, I can go through a 500 deductible, or I can go through a 1,000 deductible, right? So when you do this, you've got to split it up into those three cases. That was weird. Pardon me, I want claim when I'm done. So it would be probability of 250, probability of claim given 250, probability of 500, probability of claim given 500, probability of 1,000, probability of claim given 1,000. Those are the three paths, right? And notice again, do you see one of the terms in the denominator being exactly what the numerator is? Yep, that's what you should see in these things when you're doing them. And can we fill in all the blanks now? Yeah, that's not too bad, right? We just said that that's 9 out of 23 was 900 out of 2,300. That probably of that claim was 0.2. 250 is 8 out of 23. The probability of that claim is 0.4. The way I wrote times 4. For 500, it was 6 out of 23. That claim probability is a 3/10. And then that last was 9 out of 23 times 0.2. And I am not doing that in my head. I refuse. You can't make me, I'm not doing it. I would multiply top and bottom by 23 first and get all the way to 23, but still not doing it in my head. Okay. That was better than the last one, wasn't it? I think. This would be an example of a good test problem. Okay. That was pretty straightforward. You've got 3 distinct classes of things that you break your denominator into, and it's a good illustration of flipping things around. This is a good test problem. The previous problem, not such a good test problem. Not at least, not for our purposes. Actuaries might think it's a good actuarial exam problem. That I'm not going to argue with them about that. It's not a good test problem for learning the material the first time, in my opinion. And honestly, my opinion is the only one that matters right now. So, and I'm guessing you'd rather know what's on my test than what's on an actuarial exam. I'm guessing. All right. Any questions on that one? Want to do another one? Yeah, let's do another one. Okay, let's look at the next one. Austin's like, no, I really don't want to do another one. No, I'm tired of it. All right. We've got automobile accidents with different proportions of vehicles that are in those particular model years and the probability that they got in an accident. You're given that you selected something from one of the 2014, 2013, 2012 model years, and it was in an accident. Probability that the model year was actually 2014. Now I notice this one's got a little bit of a twist to it, at least in my opinion. First, I would have used the word or rather than and. We're picking one car from that whole group, right? The way that we use the and, it sounds like they would pick one from 14, one from 13, and one from 12 with the or and, right? It really means or. You're picking one car. It's one of those. And then you're trying to figure out if it came from 2014 or not. Okay? So there's a little bit of a twist. We're not taking any car selected. We're just taking that it was from those first 3 years, right? Okay. So notice that we want probability of 2014 given what? Yeah, but there's a little bit more given information, right? It's not just accident, but it's accident and 2012, 13, or 14, right? It matters in how we're going to do the computation. It doesn't matter because they told us it didn't come from the other. It came from 2012, 13, or 14. That's why I said there was a little bit of a twist in there, right? Whew, sorry, pardon me. Okay. How would we rewrite it first using the conditional probability formula?
Probability of 2014. And you're set accident in 2012, 13, 14.
Okay, good. Oops. And then over probability of accident and 12, 13, to 4, 14. Okay. Right? That's how we would set it up. And then reversing the top, you'd have what? Probability of 2014. Good.
Times probability of accident and 12, 13, 14. Given 2014.
Yep, good. Okay. I know there's a lot going on in the accident and 12, 13, 14, but notice what your given information is in the second, this piece here. It is 2014, right? If you're in 2014, do you satisfy this part? Yeah, I satisfy this piece, right? I'm in 2013, 12, 13, or 14, right? So really all I know, if I'm given 2014, what do I need to figure out for this whole piece? They're probably the accident given the 2014, right? I don't need to worry about this part because it's already satisfied by the given. So what's this number going to be?
0.05.
0.05. Good. Okay. Probability of 2014. It's 0.16, right? They tell you that 16, this is proportion. So 16% of the vehicles are from 2014. So that part's pretty easy, right? So far, so good? The last part's not too bad either, because you want accident and one of the possibilities. Accident and 12, or accident and 13, or accident and 14, right? That's really all we need to do for the next part. How can I get to accident and 12? What would that be? Oops, let me write that line above it. 2012, probability of accident, given 2012, good. And then do the same thing for 13. And 14. I can slide over. And again, notice that this piece right here that I'm underlining is going to match what's in the numerator, right? That last piece is going to be the 0.16 times 0.05. What are the other two pieces going to be? 0.2, yeah, 0. So the 2012 is 0.2 times 0.03, which is what you said. And the 2013 was 0.02. Yep. That problem was worded a little strangely, but basically it was the same thing as we did in the previous problem. Right? It was worded a little bit strangely. We had to be a little bit careful because we ignored the entire other group, but it was pretty much the exact same problem. Okay? Feeling a little better about them? Understand why I never bother writing the theorem down? I don't see the point. All right. So let's switch gears a little bit and go on to the next section. I did not ask you to watch a video on that one yet. There is a video for the next section to start. We're just going to start it today a little bit and then keep going on Tuesday. While I'm thinking about it, just as a reminder, our first test is 2 weeks from today. All right. So we've talked about basics of probability. What we're going to do in this chapter is start collecting some specific distributions, what we call probability distributions, that pop up in lots of different scenarios that we are used over and over and over and over again. So in chapter 2, we do things that are referred to as distributions of the discrete type. We've talked about the difference between discrete and continuous. So some examples of things that would be discrete would be maybe you are running a call center and a certain number of calls come in at different times, and you want to make sure you have enough staff to generate, cover the calls that are coming in. And so when you call someplace, it doesn't say the current wait time is 46 minutes or something along those lines, right? So you might know how many people typically call in a given time period. And so you want to know what the probability is that maybe more than a certain number happen, so that you make sure that you have enough staff, for example, depending on the situation. Okay. That's a type of a discrete distribution because we're talking about number of people entering during a time period. Okay. That's an example of a discrete distribution. We call that one a Poisson distribution, and we'll talk about that in a later section. All right. So as far as the problems go for random, the whole title of the section is random variables of the discrete type. Let me give you a definition of what we mean by a random variable. A random variable, typically we refer to it with the letter X. Now, we call it a random variable and give it a name like it's a variable, but we really mean a function. Okay? So a random variable X is a function. What does it go from? Well, it goes from a sample space to the set of real numbers. Okay? So S is the sample space of some experiment, random experiment. And of course, R is just the real numbers. Okay. Now, that's all we mean by a random variable. It has to satisfy some situations, but I said it goes to the real numbers. For the discrete case, pardon me. For the discrete case, this is going to turn out to be associating a probability to each element in the sample space. So it's going to have to be between 0 and 1. This is going to be a probability. In the continuous case, you can have numbers that are bigger than 1, because basically it's going to be a weighting function. How heavy is something on one end versus another. So it could be really, really big, because we'll calculate probabilities in a slightly different way when we do continuous functions or continuous distributions. But it still couldn't be negative, because I can't have a negative weight associated to some event, right? So it'll still be positive. So even though I said this is going into the real numbers, we're never going to assign a negative real number to a random variable. So all we mean by random variable is some function, okay? Pardon me. So we're going to plug in things from the sample space, put it in the function, and have some weight assigned to it. For the discrete random variables, that weight that's assigned to the event is just, or the thing from the sample space is just the probability that thing happens. Okay. So be a pretty straightforward concept for us. Now, again, usually we refer to these functions as, or in a slightly different way. So in this example here, this first example that we have, notice it's asking us to determine the constant C so that our f of x here satisfies the conditions of being a random variable. All right, so PMF, this stands for probability mass function. I think I said something incorrect when I was talking about random variables a minute ago. Oh, I did say something wrong when I said random variables. I'm going to go back to that. I was talking about probability mass function property. My bad. Try that again. Your random variable literally does, I apologize. Ignore what I said about what random variables talked about earlier. I was thinking about what I'm talking about here in a second. Random variables quantify experiments. What the event might be flip heads. The random variable assigns a number to flipping heads. Okay? The event might be draw a card from a deck of cards. The random variable would just give a number to that. Okay? That's what the random variable does. So ignore what I said. It just assigns a real number to an event. Okay? The probability mass function does what I told you it was going to do for us. So probability mass function takes that event that's been quantified, given a quantity number, given a number, okay, given a number, and then plugs that number in and assigns the probability to it. So there's kind of a two-step process, if you will. whatever the events are, we're going to assign numbers to them, and then probability mass functions takes those numbers and assigns probabilities. Okay? So your probability mass function can't be negative, can't be greater than 1. And for the discrete case, when you plug in a number, it gives you the probability. Okay? So when it's asking you to figure out these constants that make it a probability mass function, well, in particular, could this C right here be negative? No, none of it's going to be probabilities. If we plug in all of these numbers and add them up, what better we get when we're done? 1. If it's going to assign probabilities when I add all those up, it better get 1, right? So that's how we're going to figure out what the constant is, okay? So if we take our sum, and I'll write it this way, for a probability mass function, a couple of conditions that you need is that when I put in anything, it has to be greater than or equal to 0, no matter what. Oops. For all x. I'll just write it for all x instead of trying to say where it's from. And then the second condition is that if I add up everything from my sample space and plug it into the function, I better get 1. There's another condition as well, but we'll talk about that in a second when we start doing, or on Tuesday, when we actually start doing probabilities. So for our purposes, for part B, the function they give us is some constant times x. We want that to be 1 when we're done. Well, if c is a constant, we can just pop it out in front. Now, you could literally add those numbers together. 1 plus 2 plus 3 up to 10, but there's a formula for that. May or may not have seen that formula before. If you do if I add up I, the first sum of the first n integers, the formula is n times n plus 1 over 2. X is playing the role of my I here. Okay. We get 55, I think. So C will be 1 over 55. So that's the constant that you would need to make it a probability mass function. Well, you could do the same thing for part E there. It's the same kind of idea, except that it would involve whatever the n is, right? Basically, E is the same problem as B is. The only difference is you got 1 over C rather than just a C, but it's literally the same problem, right? So in any event, I'll do C and F on Tuesday. Notice that both of those are infinite sets. Still a discrete random variable. It's just an infinite discrete random variable. The first one involves doing a geometric series. The second one involves doing partial fractions. So it's a good review from stuff that you talked about. So we'll do those on Tuesday. If you haven't already, I was going to give you homework too. Wasn't I? Almost got away with it. So I'll give you some homework to work on. So if you don't remember geometric series and don't remember partial fractions, I'd go back and look at that. This is on page 33. And this one's going to be a little bit longer because it's got 2 sections to it. And then page 38, 3, 8, and 9. The first section is, what is that, this 13th? The first section is the independent events section that we did. And the second one is the Bayes theorem problems out of the book. All right. So what are we doing on Thursday? Again, I got a video over 2.1. If you want to watch that before class, that'd be great. But also, breakout calc ideas, and remember how you do a sum of a geometric series and what you do with partial fractions. Okay. Those will pop up, especially geometric series. We will do geometric series several times. Okay. So make sure you remember that one. Partial fractions we'll use a little bit, but not horribly not much. But go ahead and review it so we can do those 2 problems at the beginning of class on Tuesday. Sound like a plan? And if you need a little bit of a refresher, you need to come ask me. I'm happy to go over geometric series and partial fractions with you at my office. I'm happy to do that. So, all right. Have a good one, everybody. We'll see you on Tuesday.